All right, day 6. What do we notice about these two pictures? Well, it looks like they both go through the origin. But the scale is so large, who knows? I also notice that they're both factorable. Let's see if that leads us anywhere. Sure enough, as I factor both of these, I get different results. In fact, I get a few x-intercepts when I set these equal to 0. Using this information, if I were to zoom in and see more details and have a better scale, I would come up with the y-intercepts and the x-intercepts. Finding the y-intercept, as usual, we set x equal to 0, and we get the corresponding y-intercepts. Looking at the factored form, we get these x-intercepts. So there's more to the graph than what we see above. Some words that we have to know. Turning point, when it goes from increasing to decreasing or the other way around. Something like our minimums and maximums that we talked about earlier. If we have a polynomial of degree n, there'll be at most one less turning point than the degree. Conversely, if we have a certain number of turning points, then the degree will at least be one more. N is one more than n minus 1. When we change concavity, we get an inflection point. And it goes from concave up to concave down, or concave down to concave up. And there's at most 2 less than the degree inflection points. So looking at this graph, we're going from decreasing to increasing turning point, increasing to decreasing turning point, and decreasing to increasing turning point. An inflection point's a little harder to see, but let me see if this will help. Let's say you're driving along on this graph, and you're making slight left turns to stay on the graph, aren't you? Then you make a sharp left turn here, and you're turning left, but at some point here, around here someplace, you start turning right. Sharp right turn, turning right. Somewhere here, though, you start turning left again to stay on the graph. Sharp left turn, and then all the way up. So there's 2 places that you're turning, changing from turning left to turning right. And those are the inflection points. In example 1 here, do you notice that if x is 0, the y-intercept is -5? Well, this has a positive y-intercept, so that's no good. The leading term here is positive, so the right hand goes up. Here the right hand goes down, so that one's no good. So this one, the right hand goes up, that's good, but we have 4th degree here, and we have 1, 2, 3, 4, 5 turning points. We can only have 3 turning points maximum with a degree of 4. So that one's no good. This one's left, right hand up, negative y-intercept, and 1, 2, 3 turning points, and its 4th degree. This looks very good. So let's summarize that. Negative y-intercept, right hand up, and 3 turning points since its 4th degree. Those are the keys to help us choose which one is which. So now we're going to talk about the zeros of a polynomial function. They are the x-intercepts. Here they cross, here it touches or bounces, and here it crosses again. Since the graph is continuous, it is connected. The intermediate value theorem says between consecutive x-intercepts, the graph must be entirely above or below the x-axis. So between these two intercepts, the graph is above entirely. Between these two intercepts, the graph is below all the time. Between these two intercepts, the graph is below. And so between intercepts, we can see it's entirely above or below only the x-axis. So if a value makes the equation equal to 0, then that value is going to be called a real 0. And there is a relationship between zeros and x-intercepts. So here we factor by grouping. The first two have a common factor of x squared. The second has a common factor of -1, or just a negative, whatever works for you. I like the 1 because the next step, we have a common factor of x plus 3. We take that 1 out, that one common factor, and we have left the x squared and the -1. Factor the difference of squares, and we get the x plus 1, x minus 1. Set each of these equal to 0, and we get these 3 zeros. -3, 1, and -1. B is very much the same thing. 4 terms, factor by grouping. In C, factoring out a negative x squared makes this easy to factor. X minus 2, x minus 2. We set this equal to 0. You can see that x equals 2 will make that 0. Don't forget, though, that this x in front can also make this expression equal to 0 because you're multiplying. And D is the same as C. The pattern here that you might notice is if it's an even exponent, then it touches. If it's an odd exponent, like this one is, it goes through or it crosses. This is even, it touches. So even, touch, odd, cross. Here it's odd, it crosses, but it crosses like a third-degree equation. Remember those third-degree equations we graphed in the past. First degree, odd, it goes through. second degree, it touches. So multiplicities just counts how many times something occurs. If the factor occurs a certain number of times, we could also say that the 0 appears that many times. So here it crosses, odd multiplicity, here it touches, even multiplicity, crosses, odd multiplicity, crosses, odd multiplicity. I know this looks like it touches, but it also goes through, so we say it crosses from positive to negative or negative to positive. So I hope you can see here that the -4 appears once, the 3 appears once, and the 10 appears once. They want the value of the zeros and the multiplicity. And since the right hand goes down, the sign of the leading coefficient should be negative. So, to write this out, the -4 gives us x plus 4, the 3 gives us x minus 3, and the 10 gives us x minus 10 for the factors that they came from. But if I were to multiply that out, I would get x cubed blah blah. To make the right hand go down, I must also provide this negative sign. So that would be negative x cubed blah blah.